Hello there, this is your lecture for Chapter 7, which is all about probability and samples, and this thing called the distribution of sample means. This is the last chapter before we get to hypothesis testing, which is my favorite part of this class, where we start to figure out what does statistical significance mean, and how can we make inferences about the population based on samples, or inferential statistics. So this will be the last part of the descriptive statistics portion of this class, and then we'll be moving on to inferential statistics or hypothesis testing. So just as a kind of a quickie review, in the previous two chapters we covered the z-distribution. Remember, it has a mean of 0 and a standard deviation of 1, and it has the same shape as the population distribution. So just because you convert scores into z-scores doesn't change the shape. We also looked at how to convert x values into a z-score and how to convert z-scores back into an x value with the formulas that you see on the screen. Then we also talked about how to determine the probability of selecting a score, not using the unit normal table, but just using the frequency distribution in general. So just the raw scores. So remember, that's the probability or proportion is the number of a specific outcome divided by all the possible outcomes. And then we wrapped it up with how to determine the probability of selecting scores within a specific range using z-scores and the unit normal table. So really, as an example, the probability of randomly selecting a score greater than 5 from a population with a mean of 4 and a standard deviation of 0.5. So here's x. You need to turn that into a z-score. Here's the math for that using the z-score formula. So here's the x value, 5, minus the mean for the population, 4, divided by the standard deviation for the population, 0.5. You end up with a z-score of 2. And then if you think about it, if we have a mean of 4 in the middle, and we're looking for the probability of randomly selecting a score greater than 5, that would be the tail of the distribution. So you would use that z-score to find the proportion in the tail, and your answer would be 0.0228. Or in other words, you have a 2.28% chance of randomly selecting a score greater than 5 from this population. Another way that you could say this is that 2.28% of scores are greater than 5. So that's where we've been. We're going to be moving on to looking at more than just z-scores for a single x value. So although applying the concepts of z-scores and probabilities to single scores is great for the illustration of these concepts, in actual research we rarely care about single scores. We care about samples. So multiple people taken from the population. Because think about it, one person is not going to be a very representative sample of the population that they're drawn from. And we're moving on to inferential statistics, where we're collecting sample data and using those results to make informed decisions or inferences about the population. So because we want to make generalizations about the population based on samples, the rest of the semester is going to be devoted to samples. Specifically, sample means, as opposed to single scores or x values. So instead of examining the probability of obtaining a score or a range of scores from a population, we're concerned with the probability of selecting a certain sample from the distribution of all possible random samples of a specific size from the population. So, to put it differently, instead of comparing a single x value to the distribution or all the scores in the population, we're going to be seeing how likely it is to get a specific sample mean from all of the possible sample means that you could have from this population. So now, since we're moving on from working with the population distribution to looking at the sampling distribution, we have a different measure of variability. So instead of working with the standard deviation, which is just the average distance between all scores or all x values and the mean, instead of working with that standard deviation to determine variability, we are going to be working with something called the standard error. And the standard error is the average distance between all sample means of a specific size and the population mean. Or in other words, the difference to expect between the mean of any given sample and the population mean. So, you've probably heard that before when we talk about sampling error. Remember, sampling error is just the difference between a population parameter and a sample statistic. Well, the standard error is a measure of sampling error that tells you, on average, how much of a difference would we expect to see between any given sample mean and its corresponding population. So there's a problem with samples. Samples are variable. They have different individuals with different scores and different sample means. So sample means often differ from the population mean, and that's that whole sampling error thing. And that's what the standard error will be telling you. So we're moving on from standard deviation to standard error. So let me use a very oversimplified example of a sampling distribution to just show you what the contents of a sampling distribution are. So I can say all day the sampling distribution is every single possible sample mean of a specific sample size from a population, but actually showing you how you could derive that will help you understand it. One kind of thing I want to note before I go through this slide is I'm never going to ask you to generate every single possible sample of a specific sample size from a population. This is simply just to show you where the distribution of sample means comes from. In reality, we're never going to have this small of a population, and we'll probably never have this small of a sample, but there's this thing called the central limit theorem that allows you to know the characteristics of the sampling distribution without going through this whole process. And we'll talk about the central limit theorem here in a minute. So for any given population, there are typically a huge number of samples that can be drawn from that population. Normally, one thinks of sampling from relatively large populations, but the concept of the distribution of sample means can be illustrated with a small population. So here's the small population that I'm going to use to illustrate the distribution of sample means. Another word for the distribution of sample means is the sampling distribution. All right, let's say that we've just got 3 people in our population. One has a score of 3, one has a score of 4, and one has a score of 5. And here's the mean and standard deviation for this population. Well, remember, the distribution of sample means is every single possible sample mean of a specific sample size from a single population. Well, here's our population. Let's say that our sample size is 2, and we need to find every single possible combination of 2 numbers, sample size of 2, from this population, and then find the mean of each combination of numbers. And then that would be your distribution of sample means. So I'll walk you through it. Remember, we're going to assume random sampling with replacement in this class. So you need to have every single possible combination of the numbers, one number coming first and one coming second. So not only do you have 3 and 4, but you also have 4 and 3. These are the same 2 people, just in a different order. And you can also have the same selection twice in that single sample. So you'll see, 3 and 3. Because remember, 3 is being drawn, then it's replaced. And then the next selection's taken. You could technically have the same selection twice. Again, I'm never going to have you create a table like this on your own. This is just a demonstration. So here are all the possible 2-number combinations from 3, 4, and 5, this population. And then here are the means for each one of those. So the mean for the first sample, 3 plus 4 divided by 2 gives you 3.5, and so on and so forth for all of these means. Now, I turned these means, this is the data I'm working from, into a frequency distribution table so that I can then turn it into a graph. So I look at my means and I have a range from the highest is 5 and the lowest is 3. So I represented that here, everything from 5 to 3. And you see, there's some 0.5s going on here, so I want to capture those as well. And then I count how many I have. Well, I have 1 mean of 5, 2 means of 4.5, 3 means of 4, 2 means of 3.5, and then 1 mean that's 3. These are just all the means from all these possible 2-number combinations, sample size of 2, from this population. And just for kicks, I went ahead and put the proportion of means that are 5, or the probability of randomly selecting a sample with a mean of 5 right here, because eventually we're going to be looking at tables to find these probabilities, because we're not going to have access to all the entire population and all the possible sample means. This just shows you that when you have a relatively small population and a small sample, you can find these probabilities or proportions through calculations and not using the table. So based on this frequency distribution table for all of my possible sample means of a sample size of 2 from this population, I created this picture here. And we'll talk about the central limit theorem and what it tells us about the shape of the distribution in a little bit. But for now, I just want you to note that this is a normal distribution. So now let's look at central tendency, specifically the mean, and variability, specifically the standard error now. Remember, we're moving on from standard deviation to the standard error. Let's look at those here. So, another thing I want to note, you are going to be doing these calculations the easy way. So, let's start with the mean. Don't get caught up in this right here. I'm never going to have you do this, but it's a good demonstration of the distribution of sample means and the standard error. Okay. So, the expected value of the mean is also referred to as the mean for the sampling distribution. So, what would we expect our sample mean to be based on our number of possible sample means and the sum of all those sample means? The symbol for that is this U with a subscript M, but you won't be seeing this a lot because, as we'll learn about in the central limit theorem, when you take the mean of all the means, so you add all those possible sample means together and divide by how many samples you have, in this case 36 divided by 9, you end up with the population mean. Check it out. It's 4. The population mean is 4. So the expected value of the mean, or the expected value of the mean for the sampling distribution, is always equal to the population mean. This will always be the case. So I want to demonstrate that for you before I just tell you to believe me when we talk about the central limit theorem. Now there's two different ways to calculate the standard error. The only one that you're going to be using is this one down here, this standard deviation divided by the square root of n. But I want to show you that the standard error is simply the standard deviation of all of these sample means. So if you remember, we have to find sum of squares before we can find the standard deviation. And so instead of using x values, I just replace x with means. So remember, we're moving on. We're not going to worry about single x values anymore. We care about sample means. So this is the same formula that we were using for sum of squares for regular scores, just x values, but x has been replaced with m, and n is now referencing the number of samples. All right, so you could technically find this. You could take all the m's and add it together, all the means, to get 36, and then you'd eventually square that. And then just like before when we had to take all the squared versions of the x values and add them together to get this, you just square all the means and add them together to get that first value in your sum of squares, and then you carry out your calculations. And note here, there's 9 samples. You end up with a sum of squares of 3. Plug that into the standard deviation formula pretty much, right? It's just that now this is the sum of squares for the means divided by the number of means, and you end up with 0.577. Again, I want to point out this is not the process that you're going to be using to find the standard error, because in realistic situations, we don't have access to the entire population set of scores, and it's almost impossible to calculate every single possible combination of, let's say, if we had 100 people in our population and we had a sample of 30, you can imagine how much work that would take. So you don't have to have this information to find your standard error. All you need is the population, standard deviation, and the sample size that you are going to be using. You do those calculations, standard deviation divided by the square root of the sample size, and lo and behold, you get the exact same answer. This is much easier, and we can do this even when we don't have access to all our data, and I'm always going to be giving you that population standard deviation. Again, I'm not going to ask you to find all these possible sample means with specific sample size from a population, because this can be very unwieldy. It's not going to be possible to do this in any reasonable amount of time if you're working with larger populations and larger samples. Just as a side note, to figure out how many possible samples you would have from a specific sample size of a given population, you can take the population size and take it to the power of the sample size. Let's say that you had a population of 100 and you wanted to find every single possible sample of 5. That's a whole lot of different combinations of 5 from a population of 100. Can you imagine going through and finding each one of those combinations that many times and then finding the mean? It's just not reasonable. So you will not be doing this in practice. But it's important for you to understand that the standard error is just the standard deviation of all the possible sample means, and you can calculate it using this formula down here. So one thing I want to mention too, if you were working with a sample that wasn't with replacement, then you would have no repeated selections or combinations here. So you would just have the 3 and the 4, the 3 and the 5, and the 4 and the 5. That would be it. But your mean would still equal the mean for the population, and there would be a small correction in the standard error formula. But we're not going to go there. We're always going to work with replacement. So now I want to talk about the central limit theorem. And I demonstrated the shape, central tendency, and variability with the example. But now let's just talk about the rules that prevent us from needing to go through that whole process of finding all the possible sample means and doing all these calculations. So there's 3 different characteristics of a distribution: shape, central tendency, and variability. And this central limit theorem makes it possible to understand these characteristics without taking hundreds or thousands of samples. So the central limit theorem just identifies the characteristics of the distribution of sample means, or the sampling distribution for any population, no matter what the population's size, shape, mean, or variability is. So this first characteristic of the distribution, this shape. The shape of the sampling distribution depends on 2 factors. One is the shape of the population from which you're sampling from. So if the population distribution is normal, then the distribution of sample means will always be normal, no matter what the sample size is. Think about it. Even if you have a sample size of 1, the sampling distribution of the mean will be normal because it'll be just an exact copy of the population distribution. All possible scores from that population, or all possible means of a sample of 1 person, be the same thing as all the scores, just an exact replication of the population distribution. So the second thing that the shape depends on is the sample size. So if the population from which you sample is very extremely non-normal, so it's a skewed distribution, the sampling distribution of the mean will still be approximately normal given a large enough sample size. So depending on how skewed it is, if it's crazy extremely skewed, you may need somewhat of a larger sample than greater than or equal to 30. But for the most part, you're going to almost always have a normally shaped sampling distribution when you have a sample that's greater than or equal to 30, even if the population distribution is skewed. So in other words, the only way that you can have a sampling distribution that's non-normal is if you have a skewed population and you have a sample that's great or smaller than 30 people in it. And that's important because remember, the use of that unit normal table that we use to find probabilities and proportion relies on a normal distribution. And luckily, the sampling distribution is always normal, even if the population is skewed, as long as we have a large enough sample. So greater sample sizes help ensure that the sampling distribution of the mean is approximately normal. The next characteristic of the distribution that central limit theorem tells us all about is central tendency. So just remember that the mean of the sampling distribution, that's what this little symbol represents, is equal to the mean of the population. So remember, we calculated that mean here, and we found 4, and that's equal to the original population mean. And that will always be the case. So when we're drawing out our distributions, we're still going to plot our population mean smack dab in the middle of the distribution. The third characteristic of the distribution that the central limit theorem tells us all about is variability. So, variability is just the standard deviation of the sampling distribution, or the standard error of the mean. So that whole standard deviation of the sampling distribution was demonstrated through this calculation, And that just gives us the standard error, or how far away on average do we think that any possible sample mean of a specific sample size from this population will be from the population mean. But remember, you don't have to go through all this. You can find it from just using this formula right here. So there's a bunch of different ways that you can describe what is the standard error of the mean. You could say it's the standard or the typical difference of any single mean from, or sample mean from the population mean. How well should any sample mean of a specific sample size estimate the population mean? How much sampling error is there expected by chance? All of those different ways to describe the standard error are correct. If you have a large standard error, then that means that you just have very scattered sample means and big differences in means from one sample to another. So you would expect more sampling error if you have a large standard error. Or in other words, you would expect that your sample mean wouldn't be as representative of the population mean compared to a situation when you had a small standard error. That just means that all the sample means are pretty close together and you have similar means within your distribution. So you would expect that any given sample would be pretty representative of the population mean. Or in other words, it would have a mean close to the population mean. So here's just a nice summary of all the different distributions that we've talked about this semester. So we started off looking at population and sample distribution, just looking at scores, right? Scores either from everybody we're interested in or the scores from the people that we're actually studying in our sample. Now we're moving on to the distribution of sample means, or in other words, the sampling distribution. These two words are the same, mean the same thing. Now instead of looking at scores, we're looking at all of the possible sample means of a specific size that are taken from the population. So remember, all of these possible sample means of a specific sample size from the population, this would be the distribution of sample means, or the sampling distribution. So no longer just concerned with X scores, but now all the possible means that you could get. Moving on to shape. Population, typically anything that you measure in the population will be normally distributed, where most people fall in the middle and then you have extremes on either end. The sample distribution can be any shape, especially if you have a smaller sample. It's easier to get skewed data that doesn't represent the normality in the population. Then the sampling distribution, remember, that's always normal if the population's normal. And even if the population distribution isn't normal, then the sampling distribution will be pretty close to normal as long as you have 30 or more people in your sample or scores in your data set. Here are the different calculations for the mean for the population and the mean for the sample. Pretty much the same process. Add up all the scores, divide by the total number of scores. The only difference is that you have a lowercase n to represent sample size and an uppercase n to represent population size. Then moving on to the mean for the sampling distribution. So I demonstrated that here, taking all of the means for the specific sample sizes from this population, adding them together and dividing by the total number of samples. But remember, you don't need to do that because the mean for the sampling distribution is equal to the population mean. Remember, we found that here, 4 and 4. All right, variability. So before we were talking about the standard deviation. If we were working with a population, then remember we took the square root of the sum of squares divided by the population size. If we were looking at a sample, we divided by the sample size minus 1. Remember, we did that minus 1 correction in the denominator to bump this overall value up so that it would be more accurate representation of the population. Because remember, samples tend to underestimate how variable or spread out scores are in the population. So we wanted to bump this up a little bit by taking negative or subtracting 1 in the denominator. Then variability for the distribution of sample means, or the sampling distribution. This is the formula that we're going to be most concerned with. Just standard deviation divided by the square root of n. And I demonstrated that that formula is equivalent to finding the standard deviation of the sampling distribution. So using the traditional sum of squares divided by n formula, just using the means. Remember, you're not going to need to do that. You'll just be using that second formula. And just as a reminder, the standard error tells you the difference to expect between the mean of any given sample of a specific sample size and the population mean just due to chance. So how far off is our sample mean going to be from our population mean? Whereas the standard deviation just said the difference to expect between any given score, not a sample, and the mean, be it the population mean or the sample mean. The z-scores, different calculations. So when we were looking at z-scores from a population, we took a specific x value, subtracted the mean for the population divided by the standard deviation of the population. So we said, okay, what's the difference in terms of the raw scores between a specific score and the mean of all those scores, and then compared that to the standard difference between all the scores and the mean for those scores. Same sort of rationale here, only if we were comparing a score to the sample distribution, we would look at the sample mean and the sample standard deviation. Now z-scores for samples, whereas this was the z-score for specific x values, we move on to calculating z for specific sample means. We have the sample mean minus the population mean divided by the standard error, not just the standard deviation. So you'll need to use this formula up here, the standard deviation divided by the square root of n, to find the standard error. So instead of saying, how far away is the specific x value from the mean? Okay, well, how far away is it in terms of the standard distance? Now we're going to say, how far away is this sample mean from all of the possible sample means that we could get, or remember, it equals the population mean, and then compare that to the expected difference just due to chance between any given sample and the population. Now, the standard error depends on two things. So that measure of how far away do we think that any given sample mean will be from the population mean due to chance. Well, the first thing that it depends on is the standard deviation of the population. If you have a more variable population or more spread in scores in your population, you're going to have a higher standard error. The standard deviation of the population is the starting point for the standard error. Think about it. If you look at the formula up here, if n equals 1, then the standard error equals the standard deviation, just equal the same. Now, the sample size is another thing that is important to think about when it comes to the standard error. So if you have a larger sample size, you're going to have a smaller standard error. This is referred to as the law of large numbers. Just conceptually, if you have a bigger sample, it's probably going to be more accurate representation of the sample or of the population, so you would have a lower standard error. You would expect that your sample mean and population mean would be closer. So again, larger samples are more accurate representations of the population, and as n increases, just thinking about the calculation, as n increases in the denominator here, then the overall value of the standard error is going to decrease. As this gets larger, this gets smaller. As this gets larger, this gets larger. Think about the rules with fractions. As the denominator increases, the overall value decreases. As the numerator increases, the overall value increases. So now let's look at an example of how the standard deviation has an impact on the standard error. All right. So let's say that we have a population of drivers and they have a mean number of speeding tickets of 10 and a standard deviation of 1. So this is a very low variability population. Most people have between 9 and 11 speeding tickets in this case. Okay, so now let's see. If we had a sample of 10 drivers from this population, how well on average would we think this sample would represent the population? Or in other words, how close do we think the mean number of speeding tickets in this sample would be to the mean of 10 in the population? So we're looking for the standard error. So let's use that formula, that easy formula that I've been talking about for the standard error, which is the standard deviation divided by the square root of n. our standard deviation is 1. Divide that by the square root of 10, our sample size. And we end up with 1 divided by 3.1623. And that gives us a standard error of 0.316. So on average, we would expect that the mean number of speeding tickets from this sample of 10 would be off by about 0.316, or be 0.316 points away, or tickets away, from this mean of 10. So, with a sample of 10 drivers and a standard deviation of 1, our estimate of the population average of speeding tickets would be off on average by plus or minus 0.316 points. So we could overestimate it on average up to 10.136 or down to 9.684. So in other words, 10 plus 0.316 or 10 minus 0.316. So I'll put a little note of that here. So, anywhere between 9.684, which is 10 plus the standard error, to 10.316, 10 minus the standard error. Okay. Next one. We still have a population of drivers with a mean of 10 speeding tickets, but now our standard deviation is 5, so it's higher than 1. So this is a more variability in our population. So in this population, most drivers have between 5 and 15 speeding tickets. We're still randomly selecting a sample of 10 from this population, and now we still want to see how far off will our sample mean be from our population mean of 10. So, to calculate our standard error, we're using the same formula. Standard deviation divided by the square root of n. But now our standard deviation is 5. Our sample size is still 10. So we've got 5 divided by the square root of 10. We already know that's 3.1623. And we get a standard error of 1.581. So on average, the mean that we calculate from this sample will probably be off by about 1.581 speeding tickets. Or in other words, it'll be between 8.48, so 10 minus 1 standard error, to about 11.58. 10 plus 1 standard error. And that 10 is just the population mean. So, this is quite a larger range than what we had up here when we had a smaller standard deviation and a correspondingly smaller standard error. Here, roughly 10 to 10 tickets if we do some rounding. So we'd be pretty accurate with our sample here. So in other words, we could be pretty confident that if we took a sample of 10 drivers, their mean would be close to the mean for the population. Whereas here, we're not so confident. So if we did some rounding, between 8 and 12 tickets would be the expected range that our sample mean from this sample would fall in, based on a mean of 10 and a standard deviation of the population of 5. So we wouldn't be as confident in our sample mean here when we have a larger standard deviation than we would be with the same sample size and a smaller standard deviation. So when we have a smaller standard deviation, we're going to expect less error in our sample mean, or in other words, we expect that our sample will be a better estimate of the population. Now let's look at an example of the relationship between the sample size and the standard error. All right, so this first one is identical to the one that we just did. This guy right here. population mean of 10, standard deviation of 5, and we're randomly selecting 10 from the population of drivers. Well, now let's see what happens to this standard error when we have a much larger sample size. So let's go ahead and do our calculation. So the standard error, standard deviation divided by the square root of n, 5 divided by the square root of 400 is our new sample size. This becomes 5 divided by 20. And now our standard deviation is 0.25. This is much smaller than our standard deviation was here. So we expect that our sample mean is going to be much closer to our population mean when we have a larger sample size compared to when we have a smaller sample size. So with a sample of 400 drivers, our estimate of the population average of speeding tickets would be off on average by plus or minus 0.25 points. Or in other words, we would probably have a sample mean from this sample anywhere between, 9.75 to 10.25 tickets. Pretty darn close. Not a whole lot of error going on here. So again, if you have a larger sample size, then you're going to expect that your sample is going to be more representative of the population, and you're going to have a smaller standard error. Whereas if you have a larger standard deviation, then you expect that your sample is going to be less representative of the population. Because scores are more spread out, it's going to be harder to get an accurate representation of the population with a sample, and your standard error is going to be larger. All right, now let's look at probability and the distribution of sample means. So why is learning about the distribution of sample means important? That's a good question to ask. Well, the primary use of the distribution of sample means, or the sampling distribution, is to find the probability of any given sample. You want to know how likely it is that your sample comes from, or how well it represents, a population. So in experimental research, if we administer treatment to the experimental group, we expect a very low probability of randomly selecting a sample that matches the characteristics of our experimental group, because the population at large has not been exposed to our experimentally manipulated treatment. So let's do an example that demonstrates this concept. So some of you have probably heard of this thing called Kaplan. They charge a lot of money to help you do better on standardized tests like the SAT and the GRE. So it may be important to see if taking Kaplan is worth the money. So you may want to know, do Kaplan courses improve performance on the SAT? Or in other words, are Kaplan students representative of the general population of test takers? You don't, if you are thinking about taking Kaplan or you've already taken Kaplan, you better hope that Kaplan students are not representative of the general population of test takers. You want them to be extremely better than the general population of test takers who didn't necessarily take Kaplan. So that leads me to another way you could ask this question. Does the Kaplan sample have an extreme mean based on the distribution of sample means? So there's one great way to figure this out. You can calculate the z-score for the Kaplan students and see if they have an extremely high z-score. Not just large, but large and above the mean, or large and positive. So the first step in calculating the z-score is finding the denominator for the z-formula, or the standard error. So step 1, calculate the standard error. So the standard deviation divided by the square root of the sample size is equal to 100 divided by the square root of 25. Our population standard deviation is 100, and our sample size is 25 Kaplan students. This becomes 100 divided by 5, and we end up with 20 for our standard error. Now we need to convert this mean of 550 into a z-score, or, finding the position of the sample within the distribution of sample means to see if it's extreme. So z equals the sample mean minus the population mean divided by the standard error. So this is equal to 550 minus 500 divided by 20. This becomes 50 divided by 20. And we get a z-score of 2.5. That's a pretty large z-score. I would venture to say that that's an extremely high z-score. It's more than 2 standard deviations above the mean. So my conclusion would be that Kaplan students score extremely higher than the average SAT test taker. Therefore, we can conclude that Kaplan is systematically improving test scores, and we would expect to see a similar effect in the population. So it's not just enough to say, oh, well, this sample mean of Kaplan students is higher than what we would expect to see in the population of test takers. We need to compare, well, how does that difference stack up to the difference that we would expect to see just due to chance? Just because we're taking a sample from this population, we expect that the mean for the sample isn't going to be an exact copy of the mean for the population. So it's not just enough to say, oh, the mean for the sample is higher than the mean for the population, but is it substantially higher than what we would expect to see the difference between the sample and the population just due to chance? This is saying, yes, it is. The mean for the Kaplan students on the SAT is 2.5 times higher than the difference in the mean we would expect to see, even if the SAT scores were not improved because of Kaplan. Or in other words, the difference we would expect to see just due to random chance. So I would be taking the Kaplan test preps if I saw this. Now I want to draw these two distributions just to show you how they're very different. So the population distribution is going to look like this. We've got our frequency along this axis, and then we'll have some x values and some z-scores. And let's roughly draw a normal curve. So this is our population distribution. All right, so let's draw a line at the mean in the middle. And that would be a score of 500 and a z-score of 0. And then let's just look at one standard deviation above and below. So with a z-score of 1 and negative 1 between, 400 and 600. This is the population distribution of all the scores on the SAT and the population. Now that's not the same as the sampling distribution. So let's draw the sampling distribution. So the sampling distribution. Again, frequency is represented along the y-axis. Draw a nice normal curve. The mean is still in the middle, and the mean is still 500 with a z-score of 0. But now, whereas before, these were x values compared to z-scores, now we're looking at the mean values and their corresponding z-scores. And now we are basing this on the standard error that we found to be, let's see, 20. So now, if we look at our z-scores of 1 and -1, we would have like 1 right about here, -1 right about here. And the mean for a z-score of -1 would be 480, and for +1 would be 520. So the sampling distribution, if you compare it to the population distribution, where most scores fall between 400 and 600, population distribution, compared to the sampling distribution, where most sample means of 25 students is going to fall between 480 and 520, you'll see that there's quite a lot less variability in the sampling distribution compared to the population distribution. And that's because sample means tend to be more similar than just a single random score selected from that population. And that also gets to the point that as the sample size increases, the standard error decreases, or the variability decreases. So I wanted to show that to you, how that works out. And why, when you're starting to draw your distributions now, you want to draw the sampling distribution based on the standard error, not the population distribution based on the standard deviation. All right, now let's look at another example where we're trying to figure out how likely, or what is the probability of randomly obtaining these 3 different samples with these different sample sizes from a population with a mean of 70 seconds to brush their teeth and a standard deviation of 20 seconds. So we're looking at a population where on average it takes 70 seconds for people to brush their teeth, and most people are falling between 50 and 90, that 1 standard deviation above and below. So what's the probability of randomly obtaining samples of individuals where the mean brushing is greater than 75 seconds with these 3 different sample sizes? So the first step in this is to find our standard errors. And I'm going to find 3 separate standard errors for those 3 separate sample sizes. So in group A, the standard error is equal to the standard deviation divided by the square root of n. Standard deviation is 20 divided by the square root of the sample size of 4 for that first group, group A. This becomes 20 divided by 2, and we get 10 for our standard error for group A. Group B, same formula that we used before for the standard error, but now we have a different sample size of 16. And 20 divided by the square root of 16 becomes 20 divided by 4, and we end up with 5 for the standard error for group B. Group C, the formula has not changed. Let's write that thing down. We still have a standard deviation in our population of 20, but now we're dividing by the square root of our sample size of 100. Becomes 20 divided by 10, and it's 2 for our standard error for group C. Now, as you can see here, as the sample size increased, our standard error decreased. Or in other words, when we have larger samples, we don't expect as much of an error between our sample mean and our population mean. So when we have the sample size of 100, we only expect our sample mean to be off by 2 points from the population mean of 70. Whereas when we had a sample size of 4, we were expecting our sample mean to be off by 10 points from the mean. So a lot more error expected when you have the smaller sample sizes. Okay, let's go ahead and sketch our sampling distributions now. So for A, Let's draw our normal curve. We'll say this is distribution A. Our mean is in the middle of 70. And most people are falling between 60 and 80. Because remember, our standard deviation, or our standard error in this case, was 10. Now let's look at the distribution for B. It's a little bit skinnier. The mean is still in the middle of 70. But now most scores are falling between, let's see, so within one standard error of 5, so between 65 and 75. And remember, in all of these, we're going to end up looking at the probability that corresponds to a mean greater than 75. So right about here out. So this would be like a tail. And then in this one, 75. This is also a tail, greater than 75. And then the next distribution, distribution C, looks like this. I'm going to try to make it even skinnier than distribution B. Our mean is still in the middle of 70. But now most scores are falling within 2 points of the mean. Or I should say most means are falling within 2 points of the mean. So between 68 and 72. And so 75 would be roughly here. And we're still looking at a tail because we're looking for means greater than 75. So just in looking at this, we know we're going to be looking for probability here in a little bit. But we can already see, judging by how big our tails are, that the probability is going to be a lot lower in C, a lot less of the distribution is being shaded, than in A or B. So just like when we were looking for probabilities or proportions pertaining to X values, we had to calculate z-scores and then go to the unit normal table. Well, we need to do that for this as well. So we're going to calculate z-scores for these means, the mean of 75, and then we're going to use those z-scores to figure out probabilities in the tail. Because we drew our distribution, we know we're looking for tails. And I'm going to base my z-score calculations on these standard errors that I already found. So for group A, z is equal to the sample mean minus the population mean divided by the standard error. For all of these, our sample mean is 75 and our population mean is 70. But in group A, remember our standard error was 10. So this becomes 5 divided by 10. 0.50 is the z-score that pertains to a mean of 75 in this distribution. Group B, same formula. Z is the sample mean minus the population mean divided by the standard error. Only now the sample mean is 75 and the population is still 70, but the standard error that we calculated before was 5. This becomes 5 divided by 5. 1 is the z-score for a mean brushing time of 75 in this population when our sample size is 16. And then finally, same formula for the z-score. Just like before, the only thing that's going to change is our standard error. And I'll put a little a up here. These are my different standard errors for each group. So Still working with sample mean of 75, population mean of 70. Now our standard error is 2. And 5 divided by 2 is 2.5. That's my z-score for my third sample of 100. Now remember, as our sample size increased, our standard error decreased. And because of that, we're having progressively smaller numbers for our standard error in the denominator of our test statistic, and our overall value of our test statistic is increasing as our standard error is decreasing. Remember, I said in inferential statistics, we love big values for our test statistics. And that happens as our sample size increases. So does the value of our test statistics. So far, we can see that this is the most extreme sample out of all of these. And that's because it has the larger z-score. And that makes sense if you think about it conceptually. If we're expecting that if we have a sample of 100 people, they're going to be more representative of the population compared to when we have a sample of 4 people, well, then it makes sense that it would be extremely more rare to find this relatively large sample mean compared to the population mean when we have a more representative sample compared to when we expect there to be a large difference between the sample mean and population mean because we have such a small sample like here. It's less extreme result when you have a smaller sample because you're going to expect bigger differences. You're going to have a larger standard error than when we come to here where we have a larger sample mean or sample size. We really don't expect there to be much differences. Remember, we expect most of our mean values to fall within 2 points of 70 or between 68 and 72. So this 75 would be an extremely rare result to see when we have this large sample. Well, how rare is a mean greater than 75? Let's use those z-scores to then find p-values in the tail. Remember, we're looking for greater than 75, looking in tails. All right. So for part A, we're looking for the probability of a z-score greater than 0.50, which corresponds to that mean value of 75 or more. And if we go to our unit normal table and find 0.50 for the z-score, 0.50, 0.3085 in the tail. So, equals 0.3085. All right, part B, probability of a z-score greater than 1. Remember, that's the z-score that we calculated for this mean of 75 from this sample with a sample size of 16 and a standard error of 5. So let's find this z-score of 1 in the table. There it is, proportion of the tail, 0.1587. So 0.1587. Part C, probability of a z-score greater than this extreme 2.5, the z-score that we calculated for this sample. Well, let's find z equals 2.5 in our table. Scrolly, scrolly, scroll. Keep going. 2.5, proportion of the tail, 0.0062. 0.0062. That is the proportion in the tail for this mean of 75 when we have a sample of 100 people. So in other words, it's much less likely to sample 100 people whose toothbrushing time exceeds 75 than it is to sample 16 or 4 individuals with that same speed or higher. Again, because that large sample results in a low standard error, there's a low chance of obtaining that sample that doesn't represent the population just due to chance. So just as a summary of what this lecture covered, we're no longer working with single scores or X values. We're now focusing all of our attention on working with samples that have multiple X values within them. When evaluating how likely it is to select a given sample of a specific sample size from a population of all possible samples of the same sample size from that population, we're going to be basing this probability or likelihood on the position of our sample mean along the sampling distribution. So remember, that sampling distribution just represents all of those possible sample means of that specific sample size from the population. We're no longer basing our probabilities on the population distribution. We're basing it on the sampling distribution. And that sampling distribution is dictated not only by the population mean, which falls in the middle, but also the standard error, which is our new measure of variability or spread of means from the population mean. So how far away do we think any given sample mean will be from the population mean just due to chance? And this standard error just again measures how representative a particular sample mean will be of a population mean, or how well an individual sample mean of a specific sample size will represent a specific population. Now, this is going to be very useful for hypothesis testing, which is our next chapter, which is where we'll be making conclusions regarding the likelihood that a specific sample represents a population based on its position along the distribution of sample means. I've mentioned this before, but I'm going to mention it again. Remember, if your experimental group or your sample has a mean that's on either extreme end of the distribution of sample means, then we can say that a treatment had an effect. It changed the sample in some way so they no longer represent the population. So this is a lot to take in. This is one of the more complicated chapters that we'll cover, but we'll practice this a lot, and once we get to hypothesis testing, this will be the foundation of hypothesis testing that you'll see over and over again, and you will get the hang of this, I promise.